So in Unit 9, we are going to cover stoichiometry. Um, we will talk about introduction to stoichiometry and what stoichiometry actually means, even though I believe we did very similar calculations to to using stoichiometry in previous units, specifically Unit 8. And then we will see how we can use stoichiometry or the concept of stoichiometry into doing calculations and chemical equations. So essentially, the first and the second one are interconnected together. And then we will look into limiting reactants and what limiting reactant actually means in a context of chemical reaction. And then we will look into molarity and how we can use molarity to calculate concentration of aqueous solutions. And then we will finish with percent yield. Okay? So when it comes to stoichiometry, the definition for stoichiometry is using the relationship between reactants and products to determine desired quantitative data. So by using the stoichiometric relation of products and reactants together, we can kind of project how much of the product will be yielding or how much of the reactants will be needed in order for this reaction to take place. Okay? I think you will have a better image once we do some examples. So in Greek, stoichon means element and metron means measurement. And up to this point, I think we have covered or we have used conversions using the molar mass, and that comes from the periodic table, correct? So we use the collective atomic masses of all the elements that are part of that molecule collectively, and that's how we calculate the molar mass for a molecule, okay? And then we also did conversions using the chemical formula, correct? So when we looked at something as P4O10, we use the relation or the subscript of the phosphorus within the phosphorus oxide to do the conversions, correct? And then what we are going to look at this time, we are going to look at using convergence from balanced chemical equation. And that's the concept that's sort of, excuse me, sort of new to us. And we will do some practice in Unit 9. So we will balance the chemical equation, and based on the balanced chemical equation, we are going to do some conversions between the amounts of products and amounts of reactants. Okay? So we left off last time when we did some conversions, as I said earlier, between the phosphorus and the phosphorus oxide. Okay? And if you may remember, we looked at the maximum mass of P4O10 that can be formed from a 1.09 times 10 to the power 4 kg of phosphorus. And what we said, well, phosphorus has a ratio of 4 compared to the molecule of phosphorus oxide. So what we started, or this is the kind of like sketch that we had to go through. We started with a kilogram with a kg of phosphorus, and we converted that to gram. And the reason why we need to convert that to gram, and we said that we always have to convert our starting unit to gram, because when we calculate the molar mass, the unit for this one is a gram per mole. And we use that for conversion. So in order to convert our mass into mole, we need first to convert our unit, the starting mass unit, into grams, so we can cancel out the grams. So if you may also remember what I said, even if you are not sure how to conduct the whole process to the end, at least convert the mass from kilogram, from pound, from megagram into a gram first, and then convert to moles. I think everybody should be able to do that. Okay, so what we did is we started with kilograms. We converted the kg, the kilograms, into a grams, and we said our conversion here that comes from our metric system conversion, correct? So we said converting from kg to a gram, that's right here. And every 1 kg equal 1,000 grams. So now my kg can cancel out, my kilogram can cancel out with a kilogram, and now I'm left off with a gram phosphorus. Okay, now what I need to do is I need to convert my gram phosphorus to moles phosphorus. And that's basically done through the periodic table. So the number that you see here, this is coming from the periodic table. This is the atomic mass for phosphorus. And we said we use the atomic mass as a conversion tool to convert between grams of an element to moles of that element. So what I have at this point, the gram of phosphorus now cancel out with a gram of phosphorus, and now I'm left off with moles of phosphorus. Now that's where my conversion of mole phosphorus oxide to moles of phosphorus comes into application. So we know, looking at the P4O10, we know that for every mole for P4O10, we have 4 mole of phosphorus. Looking at the subscript of the phosphorus within the phosphorus oxide. And that's basically where my conversion comes from. So now my mole phosphorus can cancel out with mole phosphorus. And I'm left off at this point with moles of phosphorus oxide. So up to this point, I've converted my mass of phosphorus into a mole of phosphorus oxide. So you're basically getting there. Okay? So now I need to convert my moles phosphorus oxide into grams of phosphorus oxide, which means I will have to use the molar mass of phosphorus oxide. So this number here, this is also from the periodic table. But this one is coming from 4 phosphorus plus 10 oxygens. Okay? All right, let me do this one down here. So for the phosphorus oxide, P4O10, the molar mass for this is 4 times 31 plus 10 times 16, which is the atomic mass for oxygen and the atomic mass for sulfur. Now you add all these together, you will have 284 gram per mole. Or if you would like to write it, you can write it this way, gram per mole. So you can use this figure as a conversions between grams of phosphorus oxide into moles, or moles of phosphorus oxide into grams of phosphorus oxide. Okay? So now mole of phosphorus oxide cancel out with moles of phosphorus oxide. Now I have a gram of phosphorus oxide. The last step that I need to do here, because I have grams, again, I started with a kilogram, I'll have to finish up with a kilogram as well. So what I need to do is I need to use my metric conversions between grams and kilograms. So for 1 kg equal 1,000 grams. So the gram phosphorus oxide cancel with gram of phosphorus oxide, and I have 2.5 times 10 to the power 4 kg of phosphorus oxide. So again, I started with a mass of the phosphorus, but using the conversion factor, or the ratio, the molar ratio of phosphorus within the phosphorus oxide, I was able to convert that into the mass of phosphorus oxide. Okay, so this is, although we're using the subscripts and the molar ratio, but this is rarely referred to as stoichiometric technique. The stoichiometry is normally referred to when you're using the coefficient in a chemical equation and generating and creating your conversion. So now we'll be using the coefficients as a conversion tool between the reactants and the products. Okay, so when we say that we're using the coefficients, well, that means that we need to make sure that we have a balanced chemical equation, right? Because in order to have the correct conversion factors between the reactants and the products, or the reactants, or between the products themselves, we need to make sure that we have the equation is being balanced, and the coefficients are added correctly. Otherwise, your factors or conversion factors will be all over the place. So number one, when we're using a stoichiometric technique, or the stoichiometric concept to calculate quantitative data, we need to make sure the equation is balanced. Okay. So we use the coefficient in balanced chemical equation to provide us with conversion factor that converts from units of phosphorus oxide to units of H2O. Okay, so now instead of calculating the phosphorus within the phosphorus oxide, we are taking this into a bigger context, which is basically calculating between substances of a chemical reaction, between either the products or between the products and the reactants or the reactants. So using the stoichiometric technique, I can calculate or I can establish a relation between the phosphorus oxide and water using the coefficient of 6. And I can also establish a relation between the phosphorus oxide and the phosphoric acid using the factor of 4. And that is very critical to industrial chemistry and commercial chemistry, because you need to know exactly, for example, in this case, how much you will need to add water in order for this reaction to take place. Okay, do I need to add 6 tanks of water? Do I need to add a 2 liters of water or 3 liters of water? So stoichiometric conversion, a stoichiometric balance is very critical to chemical synthesis overall, because it will give you an idea how much you will need of each reactant and how much of the products will be generated. Okay, so let's go back to the relations, and if we look here and we see for every, based on the stoichiometric balance, for every mole of phosphorus oxide, there is, or we will need 6 moles of H2O in order for this reaction to take place, correct? And based on the coefficient that we have here. In the same time, for every 1 mole of phosphorus oxide, we will yield, or the reaction will yield 4 moles of phosphoric acid. Okay? And then, same thing, the relation between water and phosphoric acid is 6 to 4. So for every 4 moles, for every 6 moles of water, we will be getting, or the reaction will yield 4 moles of H3PO4. So, well, what does that mean? So that means that if I start, or if I have a quantity of phosphorus oxide, if I know the amount that I'm starting with, based on the conversion factor or the using the coefficient instead of the stoichiometric balance, I can project how much phosphoric acid will be yielding. Okay, and this can be very helpful, of course. Okay, so if you start with 2.5 times 10 to the power 4 kg of phosphorus oxide, what we need to do up to this point, we need to convert that into grams of phosphorus oxide. I think we all know, and we should learn this by now. And then the grams of phosphorus oxide, we'll have to convert that into moles. Why do I need to convert that into mole? Because remember, my conversion factors is all about moles. So once I convert the grams of phosphorus oxide into moles, now I can use the relation between phosphorus oxide and water to convert the moles of phosphorus oxide into moles of water. Well, what is that relation? For every, so for 1 mole of phosphorus oxide, we need 6 moles of H2O. So that is the conversion factor I will be using. This is the relationship between the phosphorus oxide and water. So now once I have moles of water, I can make my way back, which is converting the moles into grams and the grams into kilograms. Okay? All right, let's look into how we do this in numbers. So first, I'm starting with 2.5 kilograms of phosphorus oxide. What I will do is I'll convert that into grams of phosphorus oxide using my conversion factor here from the for the metric system. So my kg of phosphorus oxide cancel out with kg of phosphorus oxide. So now I'm left off with the grams of phosphorus oxide. Now what I need to do is I need to convert my grams of phosphorus oxide into mole of P4O10. How do I do this? Molar mass. Where do I get this from? Periodic table. How do I calculate this? This is based on 431, which is the atomic mass for phosphorus. We just did that. And 10 times 16, which is for oxygen. This is for phosphorus and this is for oxygen. Okay? When you add all those up together, then you will get the molar mass of phosphorus oxide, which is 284 grams per 1 mole of phosphorus oxide. So now my grams of phosphorus oxide cancel out. So now I am left off with moles of phosphorus oxide, which is exactly what I need. Now, it's time now to convert my moles phosphorus oxide into moles of water. Well, how do I know how to convert that? It's based on my balanced chemical equation right here. And I can tell for every 1 mole of phosphorus oxide, we need 6 moles of water. Here is your relationship. Okay? So now 6 moles H2O reacts with 1 mole of phosphorus oxide. So phosphorus oxide cancel out with phosphorus oxide. Now I am left off with moles of H2O. I just need to make my way back to kilograms of H2O. So I'm going to use the molar mass H2O, which is 2 hydrogen times 1 plus an oxygen, which is 16. So that makes it 18 grams per mole H2O. So you use this one as a conversion to convert between moles of H2O into grams of H2O. So now moles H2O cancel out with moles H2O. I have a gram H2O. Now, last step is to convert that back into kilograms, because we started with a kilogram, so we have to finish with a kilogram. So you divide that by a factor of 1,000 based on our metric system conversions. Okay, so again, we use this stoichiometric balance using the coefficients from the balanced equation to calculate how much I will need of a reactants if I know how much I have from one of the reactants based on the stoichiometric relationship. Okay, so let's put it all in writing now. All the steps that we just did together. So the calculation generally would ask you to convert the amount of one substance to the amount of the other one, which are both part of a chemical reaction. So you would have a chemical equation where you have different substances reacting together to form or to yield one substance or more, and you'll have to calculate or to convert the amount of one substance to the other. So the general steps, if it starts with, if you are not given the balanced chemical equation, so you need to finish the chemical reaction and you need to make sure the equation has been balanced. I can tell you, when I give you this either on the exam or on the homework, most likely that equation, it's not going to be balanced. So you need to make sure the equation is balanced. If you're not giving the amount in a gram for the first substance that you know that you're trying to convert from, first you'll have to convert it into grams. So if you're starting with a pound, convert that into gram. If you're starting with a megagram, convert that into grams, kilograms, so on and so forth. So step number 2, you have to convert that into grams. Step number 3, converting the grams into moles. Okay? And we use that from the periodic table. And we did plenty of examples at this point. And then once you convert that into moles, then you'll have to use the relationship, the stoichiometric relationship, using the coefficients from the balanced chemical equation. That's where you'll convert your moles of substance 1 into moles of substance 2. And then you'll convert the moles of substance 2 into grams of substance 2 using the molar mass. And again, this is also from the periodic table. And then at the end, you'll have to convert your grams to this desired unit that you started with. So if we started with a kilogram, just like how we did earlier, then you'll have to finish with a kilogram, or your final unit has to be in kilogram. If you started with a microgram, then you'll have to finish with a microgram, so on and so forth. You might find this flowchart also a little bit helpful. So you start, it's basically it's a repeat of what I just mentioned. So you start with substance 1, you convert that into grams, and then once you convert that into grams, you convert that into moles using the molar mass of the substance from the periodic table, okay? And then mole of substance 1 to mole of substance 2, and that comes from the coefficients from the balanced chemical equation. And then you convert moles of substance 2 into grams, and again, using the periodic table, okay? And then at the end, you will convert your grams to the desired unit that you are requested to convert to. So let's do an example with stoichiometry, using the stoichiometric concept to calculate how much we'll be yielding from one of the products from in a chemical reaction. So aluminum sulfate is used in water purification as a coagulant that removes the phosphate and bacteria and as pH conditioner. It acts as a coagulant by reacting with hydroxide to form aluminum hydroxide, which precipitates. So the keyword here, precipitates. So we know now aluminum hydroxide precipitates, which means it's a solid, okay, material from the solution, and it drags impurities down. It drags impurity as it settles. So what we need to do first, in order to be able to use the stoichiometric relationship, we need to make sure that the equation is balanced. So we need to complete and balance the chemical equation of the reaction of the aluminum sulfate and sodium hydroxide to form solid aluminum hydroxide and aqueous sodium sulfate. And then we need to write the 6 different, now in the exam, I'm not going to ask you to write the 6 different conversion relationship or the conversion factors. I'm doing this here, so it's kind of like a learning opportunity for you to see how we can create different stoichiometric relationship. But in the exam, I'll ask you probably for just one. So we will write the 6 different conversion factors that relate moles of one reactants or products to moles of another reactant or product. And then, using one of those 6 conversion factors, we will have to calculate how much what's the maximum mass of aluminum hydroxide that can be formed if we start with 0.655 megagram of aluminum sulfate when aluminum sulfate is added to water. Okay, so let's do this one together. So first what I need to do is I need to project what are my products. Now when I have NaOH and Al2SO4, this is basically a double displacement reaction. What does it mean with a double displacement reaction? That means I have to identify my A, B, C, and D, correct? So I have to identify my A, B, C, and D. So my A in this case is aluminum 3 plus. And my B is the sulfate SO4 2 minus. My C is the sodium Na plus. And my D is the hydroxide, which is a negatively charged anion. Okay, so now what I need to do is I need to do the double displacement. So changing partners. So A will be with D and B will be with C. And this is going to be my product. So the first one I have is AlOH, and that will be parentheses 3. Because remember, Al 3 plus OH negative. This will be the swapping technique. So it will be AlOH. Now, is this a solid or a liquid or aqueous? This is going to be a solid because we have it right here. So this one, a solid material. Never forget to designate your physical state for the products. Okay. The next one that I have here is the sodium sulfate. So I have Na. I have Na2SO4. Well, how did I end up with Na2? Because remember, I have Na, positive, and I have SO4, 2 negative. Doing the swapping technique, that will make it Na2SO4. Now, is this an aqueous salt or is it a solid? Is it going to precipitate? This is an aqueous, correct? Because sodium is a group 1 in periodic table, and a group 1 in periodic table always form aqueous salts. They dissolve in water, soluble in water. Okay. So this is my first step right here, or maybe half of my first step, I should say, because now we have the completed chemical reaction or the chemical equation. But guess what? This is not balanced because if I look here, if I look at every one of those, I notice that the aluminum is not balanced. Pretty much all of them, they're not balanced. If I look at the aluminum, for example, I have 2 in my products and I have 1 in my reactants. I'm sorry, 2 in my reactants and 1 in my products, correct? Right here. If I look at the sulfate, on the other hand, I have 3 in the reactants and I have 1 in the products. If I look at the sodium, I have 1 in the reactants and I have 2 in the products. If I look at the OH, I have 1 in the reactants and I have 3 in the products. So what I need to do in order to really come up with a correct coefficient or stoichiometric relationship, I need to make sure that everything is balanced in this equation. So I'm going to start with the aluminum. So I have 2 of the aluminums in the reactants and I have 1 in the product. So what I can do is I can simply multiply this by 2. So that would make it 2 on both sides. So it is now balanced. So aluminum is balanced. But this now will change the count of the hydroxide, correct? Because this also applies to the hydroxide. So my hydroxide now is 6. And I'm going to update that one too. All right, let's do the sulfate now. So the sulfate, I have 3 in my reactants. On my products, I have just 1. Okay, so what I need to do is I need to multiply the Na2SO4 with a factor of 3. So I need to add a coefficient of 3. So now the sulfate is balanced, right? So 3 and 3. But this will also change the count of my sodium. So sodium now is a 6. Okay? So now I need to balance my sodium. I have 1 in my reactants and I have 6 in my products. So I need to multiply this by 6. And this happens to also take care of my hydroxide. So the equation is now balanced. You can double check the count of atoms for both reactants and products, but it's now balanced. So once I've completed the reaction, the chemical equation has been balanced, now I can come in and I can convert or I can establish my relationships, right? The stoichiometric relationships and come up with my conversion factors, okay? So first what I will do, I'm going to write down the relationship between the aluminum sulfate and the sodium hydroxide. And from this one, I can tell that for every 1 mole of Al2SO4, I will need 6 moles of NaOH in order to complete the reaction, right? So now if I have an X amount of Al2SO4, and I'm trying to find out how much NaOH I will need for this reaction to be completed, I can use this relationship to do the conversion, okay? So that is my first conversion. Okay, let's do the other one. So now the next one that I'm doing is I will do the aluminum sulfate with the aluminum hydroxide. And I can tell here that for every 1 mole of aluminum sulfate, the reaction will yield 2 mole of aluminum hydroxide. Right? I'm starting with 1 mole and I'm finishing with 2 moles of aluminum hydroxide. Okay, I still have 4 more to go. So let's do another relation, which is, another conversion factor, which is the relation of NaOH and aluminum hydroxide. Okay, and for this one, I can see for 6 mole of NaOH, the reaction will yield 2 mole of aluminum hydroxide. And again, I can use this as a conversion tool or as a conversion factor to convert between sodium hydroxide and aluminum and aluminum hydroxide. Okay? So now what I will do, let's do NaOH and Na2SO4. Okay? And for this one, for every 6, oops, so for 6 mole of NaOH, running out of colors, the reaction will yield 3 mole of Na2SO4. That's my other conversion factor that I can use. Okay? All right, let's use the blues. Let's use the blue now. So now I think I have also I have forgotten the Al2SO4, 1 mole Al2SO4 phosphate, and the relation with the sodium phosphate. The reaction will yield 3 moles, so the ratio is 1 to 3, Na2SO4. Okay? My last relationship that I have here is the factor between the aluminum hydroxide and the sodium phosphate. And for this one, for every 2 mole of AlOH, the reaction will also yield 3 mole of Na2SO4. So using these 6 conversion factor, I can basically convert from any one of them to calculate how much I will need or how much will be yielding of the other one if we're talking about products. And that's exactly what we're going to do in the last part of this example. So if we are starting with 0.655 megagram of Al2SO4 added to water in that treatment plant, what is the maximum of aluminum hydroxide that is going to be formed? Okay, so I can tell just by looking at this one, the relation I have here, or the relationship, is going to be between the aluminum hydroxide and the Al2SO4. Okay, so going back to the conversion factors that we just did, so this is the one that we're going to focus on. This is the one that we're going to use for our example, because it basically connects, or it's we can calculate or we can convert between the aluminum phosphate and the aluminum hydroxide. So what I'm going to do is I'm going to write up here, based on the stoichiometric balance on the coefficient factors that I have from the balanced equation, 1 mole Al2SO4 also yields 2 mole of AlOH3. So I'm going to use this relation, knowing how much the amount I'm starting with the Al2SO4, and I'm going to calculate how much of the AlOH will be formed. Okay? So let's do that together. So first I'm starting with a megagram. So what I need to do, I need to convert that into grams, correct? We said every unit, doesn't matter what unit that we're starting with, we have to first convert that into grams. So I'm starting with 0.655 megagram, and I'm going to convert that into kilograms first, right? So I need to have my kg down here and megagram down here. And the megagram equal 1,000 kg. Now, once I convert that into kg, I need to later on convert that into grams, correct? Because that's my objective here in order to start the gram to mole ratio, or the gram to mole relationship. Okay, so I need to have my gram up here and my kg down here. So I have 1 gram, 1,000 kilograms. So up to this point, this converts to grams of Al2SO4 3. Okay? So now what I need to do in order to start using this stoichiometric relationship, the mole-to-mole stoichiometric relationship, I need to convert the grams of Al2SO4 into moles of Al2SO4. Well, how do I do this? Using the molar mass. So I'm going to use the molar mass of Al2SO4 to convert that into moles of Al2SO4. Okay? So I need mole Al2SO4, and I have gram Al2, so I can cancel out the grams of Al2SO4. Okay? So every 1 mole of Al2SO4, 342 grams. Well, how do I calculate this one? Remember, we get this from the periodic table. You have 2 times the mass for the aluminum, the atomic mass for the aluminum, plus atomic mass from the periodic table, plus the 3 times for the sulfur, atomic mass, plus I have 3 times 4, so that makes it a 12. So I have 12 times the atomic mass for the oxygen. So you add all those up together, you will get the molar mass for the aluminum sulfate, which is a 342. Okay, so now what I have up to this step, I have the moles of aluminum phosphate. Now I need to convert the moles of aluminum phosphate using this relationship right here into moles of aluminum hydroxide. So I'm going to multiply that by that conversion factor. But again, because I need AlOH, moles of aluminum hydroxide, and I need aluminum phosphate down here, so I can cancel out the aluminum phosphate. So I'm going to invert my my conversion factor, okay? So I can use it and I can apply it into my in my conversion correctly. So I have 2 moles of aluminum hydroxide is produced from 1 mole of Al2SO4. Okay, mole. So now I have moles of AlOH, aluminum hydroxide. I still need to convert that into grams, correct? So how do I convert that into grams? Mole AlOH 3 AlOH 3. Okay, so moles, so then I'll have to calculate the molar mass for AlOH 3. So you'll get the atomic mass for the aluminum, the atomic mass for the oxygen times 3, the atomic mass for the hydrogen times 3 as well, add them all up together, and the atomic mass or the molar mass for the aluminum hydroxide is 78 grams per 1 mole. Okay? So now I have grams of aluminum hydroxide. What did I start with? I started with a megagram. So I need to make my way back from grams into a megagram. So what I will need to do, I'll have to multiply first kg into gram of AlOH 3 AlOH 3. And I have 1 kilogram equal 1,000 gram. I still need to convert the kilogram into a megagram. So I need to have megagram kg. And again, we're talking about AlOH 3. AlOH 3. Every 1 megagram equal 1,000 kilogram. All right, let's try to cancel out everything that needs to be canceled. So the megagram is going to cancel out with a megagram. Now I'm left off with the kilograms, right? So kilogram is going to cancel out with a kilogram. Now I have grams of Al2SO4. Now I converted the grams of Al2SO4 into a mole of Al2SO4. So I can use this relation right here. So now the grams Al2SO4 cancel out with a gram of Al2SO4. I am left off with a unit of mole of Al2SO4. And that's what I use my conversion factor. Okay? So the moles of Al2SO4 cancel out with the moles of Al2SO4. I have, at this point, moles of ALOH. But this is not enough. I need to convert the moles into grams and then convert that gram at the end into a megagram. So the mole ALOH cancel out with a mole of ALOH using the molar mass of aluminum hydroxide. Now I have grams of aluminum hydroxide. Now I just need to use the metric conversions between a grams into a megagram. So gram of aluminum hydroxide cancel out with a gram of aluminum hydroxide. Now I have a kilogram, of aluminum hydroxide. And then I just need to convert that into a megagram using the conversion factor of the metric system. So when you put all these numbers in the calculator at the end, you will have 0.299 megagram AlOH3. Okay, so this is how much of the aluminum hydroxide will be produced if we were to start with 0.655 megagrams of aluminum sulfate. Okay, so when designing a chemical process or a synthesis route for a chemical reaction, scientists, they always look at how much will be needed from the reactants to produce an X amount of the product. Okay, so ideally what you want to do when a chemical reaction is taking place is that you have all your reactants have 100% been converted into products, and you have no excess of the reactants left at the end of the reaction, because any excess of the material that is left at the end from the products will basically be considered a contaminant or impurity in your final product. Okay, so and even when we looked at the phosphorus oxide and water, we calculated how much exactly of the phosphorus and phosphorus oxide, how much exactly of the water will be needed to make the phosphoric acid, for example. So scientists, they will, or a person in an industrial setting, they'll have to use all these numbers together to make sure that when the reaction is finished at the end, they don't end up, for example, with 6 tanks of water, left somewhere that needs to be disposed. Okay, so coming up and figure out exactly how much you will need of every reactant is very critical to any chemical process. So you don't have the reaction that it's finished halfway through incomplete due to the lack of one of the reactants in your chemical reaction. Okay, so for example, if you consider basically assembling like a a production line of assembling some bicycles. So any bicycle will need a single frame and also 2 wheels, correct? So for example, if you have 12 wheels and if you have 7 frames, every 2 wheels will go for a single bicycle, as you see here. And then at the end, what you will have a short, you're short with 2 wheels, correct? And you have 1 frame left without without really converting into a bicycle. Okay, so what we have here, we have the wheels that are finished first in this assembly line. Okay, and we were able only to make 6 bicycles. So it doesn't matter even if I have 8 frames or 9 frames or 10 frames, I am limited to make 6 bicycles only. Okay, so what I call in this case the wheels, they are considered as a limiting component for my production line. Okay, because it depends on how many wheels I have, so I can get how many finished bicycles at the end. So we call that as a limiting component. Okay, that means it will determine how many bicycles I'll have at the end. So what does it mean to have a limiting component? In this case, in this bicycle example. So again, for every 1 bike, I will generate, for every 1 frame, I will generate 1 bicycle, correct? But on the other hand, for every single bicycle, I'll need 2 frames, okay? So if I have 7 frames and I have the conversion of 1 frame per bicycle, I can cancel out the frame. That means I will have ideally 7 bicycles. Okay. When it comes to the wheels, on the other hand, I have 12 wheels, but I need 2 wheels per bicycle. So the wheel cancel out with a wheel, and then I will have 6 bicycle. So the wheels in this case is the limiting component. What is the maximum amount of bicycles that I can make from this production line? I can only make 6 bicycles. So this is the maximum amount of bicycles that can be made. Okay? So even though it is the small number compared to the 7 bicycles, but this is the maximum. And I think this is when people are confused, because now later on we will do some examples using chemical equation, obviously, some examples in bicycles. When I ask what is the maximum amount of oxygen, what is the maximum amount of carbon, for example, will be generated, people will go with a large number, okay, that that we convert, that we reach from one of the reactants. But in fact, we should go with the smallest number, because the smallest number is basically the maximum amount that we can generate based on how much we have on the limiting component of the reactants. Okay. So what does a limiting reactant actually mean? It is the reactant that runs out first in a chemical reaction, limiting the amount of the product that can be formed. So once that material, once that substance is depleted in your chemical reaction, basically the reaction stops. Okay? So ideally, when you're trying to design a chemical equation, you need to make sure that both substances are about to finish at the same time. So you don't end up with an excess amount of one of the reactants, because getting rid of the excess material can be costly sometimes. Okay. Um, so why we need to always consider in the limiting reactant, or sometimes it's also called the limiting reagent, because the expense, removing, as I said earlier, removing the excess of the reacting material can be very expensive, and also the danger. So some of the reactants that you start with can be really combustible, can be explosive, can be really highly flammable. So having part of the reactants at the end, or part of the product, can be very dangerous to purify at the end. Okay, and also the ease of separation. Sometimes your product at the end is really miscible, or it dissolves in the excess and the excess amount of the reactant. So separating both the excess amount of the reactant and the product can be a little bit challenging. Okay, so when it comes to a limiting reactant example, let's do this one together. It basically spins around the same concept, which we will convert the grams of the reactants into the gram of the product. So we have the two reactant, we have the silicon oxide, and we have the carbon. Okay, so what we will need to do, we will need to calculate how much silicon we will be getting from both the carbon and the silicon oxide. Okay, and the smallest number, the smallest amount, the smallest mass that we'll be getting from either the carbon or the silicon oxide, that will be our limiting reactant. So similar to our frames and wheels. So you can think of this one as the wheel, and you can think of this one as the frame. Okay, so whichever finishes first will limit, the amount of the product that I will have. Okay, so what I will do first is I will need to establish my relation between the silicon oxide and also the silicon. So the relation between the silicon oxide and the silicon is 1 to 1. Well, what that means, it means every 1 mole of silicon will be generated from 1 mole of silicon oxide. Now, in the meantime, when you look at the carbon, it's actually 2 to 1. So for every 1 mole of the silicon generated, we need 2 mole of carbon. So what we will need to do is we will need to calculate the mass, the grams of silicon from carbon and the grams of silicon from silicon oxide. Okay, looking at both these numbers, the smallest number that I'll be getting from either the carbon or the silicon oxide, this will be my limiting reagent because I am limited by that amount. It doesn't matter how much I have of the other one. This is the maximum amount I'll be getting at the end of that reaction. So what I need to do is let's start with the carbon. So with the carbon, I have 16.9, oops, 16.49, 4491 grams carbon. But first, before I use my molar or my coefficient or my stoichiometric conversion factors, what I need to do is I need to convert my grams of carbon into moles. So, and that will be coming from the periodic table. I have grams carbon and I have mole carbon. Okay. So this one is 12.01 for every 1 mole of carbon. Okay. And now once I have that converted into moles of carbon, now I can use my relation or the conversion factor that I have here, which is 1 mole of silicon will be generated or will be produced from 2 moles of carbon. Now I have moles of silicon, but I need to convert the moles of silicon into grams of silicon. Remember, we're starting with grams of carbon, so I need to finish with a gram of silicon. Okay, so now I have to use the atomic mass of silicon from the periodic table, which is 28.09 gram silicon. Okay? Now, doing all these numbers together. Okay, let's do this. So, gram cancel out with a gram carbon. Now I have moles carbon. It's going to cancel out with a moles carbon. Now I have mole silicon. Cancel out with a mole silicon. Now I have gram silicon, and that's exactly what I want, gram Si. Okay? And the number will be 19.28 gram of silicon. So this is how much silicon will be produced from the 16.491 grams of carbon. Okay? So now let's do the same thing, but now for the silicon oxide. So with the silicon oxide, I'm starting with 32.654 grams of silicon oxide, or silica. Okay, so this one will be 32.654 gram of SiO2. I need to convert that into mole, so I can use my stoichiometric factor relationship, okay? So now I need to convert that into moles. So I have gram SiO2. Up here, I have mole SiO2. How do I figure this one out? By calculating the molar mass SiO2, which comes from the atomic mass for the silicon, which is 28.09, plus for the oxygen is 2 times 16. You add those together, and the molar mass for the silicon oxide is 60.1 gram of silicon oxide for every mole of silicon oxide. Okay? So now I have moles of SiO2. Now it's the time to use my stoichiometric relationship. Time for every 1 mole SiO2, I will be getting 1 mole of silicon. And then I will multiply that into grams of silicon. Again, I'm trying to get my numbers at the gram because I started with grams of silica or silicon oxide. So this will be 28, similar to our previous last step, gram SI. And down here is mole SI, 1 mole. So now oops, come on. All right, let's do the red one. All right, let's do gram silica will cancel out with a gram. Now I have moles SI2, so I can use my stoichiometric relationship. This one cancel out together. Now I have mole of the silicon cancel out with a mole. Now I have a gram. And then my answer will be 15.264 gram silica, or silicon, I'm sorry. So now this is the amount that we'll be getting for silicon, using the silica oxide, which is 15.264. For the carbon, it's 19.28. What is the maximum amount I can get of silicon based on the amount of carbon and silica oxide? I will be getting 15. This is my maximum amount that can be generated or produced. As a result, this makes the silica oxide my limiting reactant, because the silica oxide will finish first in the reaction, giving the small amount of the silicon. So that makes it the maximum amount that can be generated, just like the example of wheels and frames. Okay? So a limiting reactant, well, how to find out what is, and if you're doing a limiting reactant example or problem or not. First, you're given two amounts of reactants in a chemical equation, just like what we did earlier with the silicon oxide and the carbon. And you will be asked to calculate the maximum amount of the product. So the moment that you see I'm asking about the maximum amount of product, you should think of the limiting reactant calculation, similar to what we did. Okay? First, you have to do two separate calculations for the maximum amount for both reactants, just like with the carbon and the silicon oxide. The smaller amount would be the maximum amount of the product that can be formed from that given amount of the reactant. And that would also be considering that this will also be considered as a limiting reactant. All right, let's do another example for the limiting reactants. This time we are looking at titanium carbide, TiC. The titanium carbide is considered one of the hardest of the known metal carbides. It is normally made by heating titanium oxide, TiO2, with carbon block at really high temperature, which is about 2200 degrees C. And this is the equation right here. So we have titanium oxide reacting with carbon to form titanium carbide with carbon monoxide. We would like to find out what is the maximum amount of titanium carbide. So we're looking at this guy here. So once we see maximum mass of one of the products, that means we are talking about limiting reactant. What is the maximum amount of titanium carbide that can be formed from a reaction of 985 of titanium oxide? That's number one. And 500 kilograms of carbon. So this is number two. And then once we determine which one is the limiting reactant or which one will give us the maximum amount, we'll have to find out why that material specifically was selected to be in excess. Okay? Because remember, when we're talking about, and that's something maybe I forgot to mention, when we talk about something that is a limiting reactant, on the other hand, the material that remains in a larger amount or remains in the reaction without being reacted, we call that one material in excess. So for example, if you look, let's go back to this one here. So when we're talking about the silicon oxide and carbon, silicon oxide, or the silica, was the limiting reagent. Carbon, on the other hand, it is considered the material in excess because that's the material that remained, some of that material remained at the end without reacting completely. Okay, so carbon is in excess, silicon oxide is the limiting reactant. Same here, same idea. We'd like to find out which one is the limiting reagent and the other material will be the material in excess. Okay, so let's look at our equation. And it is a balanced chemical equation, so we don't have to worry about that one. And then what we need to do is we need to calculate the mass that can be generated of titanium carbide first from the titanium oxide, from the TiO2. Okay, so I'm going to do that one first, and then we'll do the carbon, compare the masses that we get from each. The smallest mass that we get, that will be the maximum amount that we can produce from that reactant, and that material will be the limiting reactant, and the other will be the excess. That's basically a summary of what we are going to do. So let's do it together. So first, let's look at the titanium oxide. So TiO2. So I'm starting with 985 kg of TiO2. Well, what do I need to do first? I need to convert that into grams. I think we should all know this by heart at this point. Okay, so now I have kg TiO2, and I have grams TiO2, titanium oxide. I have 1 kg equal to 1,000 grams. So now I can cancel my kg later. So now I have grams of titanium oxide. Next thing I need to do is, in order to use my relation or my stoichiometric relation, I'll have to convert that into moles. Okay, so now I have mole titanium oxide, and I have a gram of titanium oxide. Now, for the titanium oxide molar mass, it's 79, so it's 1 mole, 79.9 grams. So now I can cancel out the grams with the grams later. Now I have moles of titanium oxide. Now I can use my stoichiometric relationship, correct? And based on that one, I'm trying to convert into titanium carbide. Mole of titanium carbide. And down here, I should have mole of titanium oxide, so I can cancel it. Okay? So based on my balanced chemical equation, the relationship is 1 to 1, correct? So every 1 mole of titanium carbide will be produced from 1 mole of titanium oxide. Okay, so now I have moles of titanium carbide. What I can do now, I can convert that into grams, correct? Based on the molar mass of titanium carbide. So I have gram titanium carbide, and I have mole of titanium carbide. Every 1 mole equal 59.9 grams. Okay, I'll let you do the calculation for the molar mass for the titanium carbide and also for the titanium oxide. I think we did plenty of them at this point. Okay, so now I have grams of titanium carbide. I did start with kg. So then I need to convert my grams into kilograms. Okay, so I have kg titanium carbide, and I have grams of titanium carbide. I have 1 and I have 1,000 based on my metric conversion. Okay, let's cancel out the units here just to make sure that we're going to end up with kg of titanium carbide. So I have kg titanium oxide, cancel out with kilograms titanium oxide. I am left off with grams of titanium oxide. That one is going to cancel out with my molar conversion, or the molar mass. Now I have moles of titanium oxide, which will cancel with mole of titanium oxide. Now I've reached mole of titanium carbide, which is going to cancel with a mole of titanium carbide using the molar mass relationship. Okay? So now I have grams of titanium carbide up to this point. Now I can cancel that one with the grams of titanium carbide, and then my answer at the end will be 738 grams of titanium carbide. So I'm gonna box this one up and keep it here for a second, because I'll be comparing that to the kilograms. Oh, I'm sorry, this is kilograms. kilograms of TiC, titanium carbide. I'll be comparing that to the kilograms I'll be getting from carbon. Okay, so let's repeat the same process for carbon now. Okay, so I'm starting with 500, let's start here, 500 kg of carbon. I need to convert that into grams first. So grams of carbon. I have kg carbon. I have 1 kg equal to 1 kilogram equal to 1,000 grams. Multiply that by, now I have grams of carbon. I need to convert that into moles before I use my stoichiometric relationship using the coefficients. So in order to convert the grams into moles, I have to have mole carbon up here and a gram carbon down here, so I can cancel out the grams. Every 1 mole of carbon equals to 12.01 grams. Again, where do I get this number from? From the periodic table. Okay, now I have moles of carbon. Now I can use my stoichiometric relationship. And based on the balanced chemical equation, I can see 3 carbons. The relation is a 3 to 1, correct? So I need to have titanium carbide up here, mole. And down here should be mole of carbon, because I'm converting from mole of carbon to mole of titanium carbide. And the relationship is 1 to 3, based on the coefficient from the balanced chemical equation. Now, I have moles of titanium carbide. What I need to do is I need to finish up just like how I did in the last stretch here in the first step. Okay? So I need to convert the moles of titanium carbide into grams of titanium carbide. Mole titanium carbide. Okay? So based on the calculation of the molar mass for the titanium carbide, this one is 59.9, and this one is 1 mole for every 1 mole. Okay? Now, I have grams of titanium carbide, but this is not enough because we started with a kg, so I need to finish with a kg. And also, I have my unit here in kg, so just to be consistent. So I need to convert the grams into kilograms. So I have kg titanium carbide, and I have grams of titanium carbide. 1 kg equal 1,000 gram based on my metric conversion. Now let's cancel out the units that doesn't need to be there. So kg, kilogram of carbon, will cancel out with kilogram of carbon. Now I have gram carbon. I'm canceling that one with the with the atomic mass conversion. So now I have moles of carbon. Once I have reached moles of carbon, now I can use my stoichiometric relationship. So I can cancel out the moles of carbon with the moles of carbon, and I convert my number at this point into moles of titanium carbide. Okay, now I need to convert the moles of titanium carbide into grams of titanium carbide. Okay, so this will cancel out with this. Now I have grams of titanium carbide. Cancel out with the metric conversion between grams to kilograms. So So grams of titanium carbide cancel out with the grams of titanium carbide. Now I am left with kg of titanium carbide. The answer for this one is 831 kg TiC, titanium carbide. Okay? Put this one in a box. Now comparing these two to each other, what is the maximum amount I can get for titanium carbide from this reaction is the 738. Because the titanium oxide will be depleted first in this reaction, leaving us with an excess of carbon in this reaction. Okay, so I am limited with my product on how much titanium oxide that I have. So the maximum amount will be the 700. This is the 700. This is the maximum amount. Okay, so this makes the titanium oxide as the limiting reactant, and carbon is the amount in excess. Okay, so the reason why we have the carbon in excess, because carbon is usually easy to get rid of either through burning, because you can always convert that into carbon monoxide and carbon dioxide. So it will be easier and more cost effective to have an excess of carbon than have an excess of titanium oxide, for example, because titanium oxide, first, it's very expensive compared to the carbon, and second, to clear or clean the reaction from residual of titanium oxide can be very costly also. So it's always better to have an excess of carbon, which is something that is readily available and is very cheap, than you have an excess amount of titanium oxide. That's why carbon was chosen to be the amount in excess. Okay, so this basically completes the limiting reactants. Let's now get into the percent yield. When it comes to the percent yield, in many cases, when a chemical reaction actually takes place in a lab in general or any industrial setting, the actual material produced is rarely, matches the theoretical amount that is being calculated. So all the calculations that we have been doing when it comes to the stoichiometric relationships and conversion factors, all these considered as theoretical calculations. Okay, so the chemist or the scientist can kind of expect exactly how much he is supposed to be getting, if this reaction were to take place. Okay, now many reasons can contribute into a low yield, an actual like a low actual yield, in the lab. That could be reversible reactions that it's happening, in the reaction pot. It could be also side reactions. Remember, when all these substances are added together, there is also catalyst and other molecules have been added. So these can also contribute into a side reaction or a slow reaction. So if the reaction is not performing really at the optimum conditions, and it's not really been driven at the fast or at the rate that it's being expected, that also can contribute into a smaller yield, actual yield, or which is the most common one, is the loss of the target material during the separation and purification process. So, as we talked about earlier, during the limiting reactant, the excess material, it's sometimes it's a little bit challenging to separate from the target compounds in the chemical reaction. During that process, if the purification process is not being conducted carefully, you can always lose some of your target compound. Okay, so for percent yield, we compare the actual, which is the amount that was produced in the lab, okay, when that chemical reaction, took place, and we compare that to the theoretical. So the theoretical is the amount that we have been calculating. Okay, so in general, when I ask you, or if anyone asks you about the percent yield, the actual yield, this will be given in the question, because obviously this is not something that you can calculate. So the theoretical, this is the amount that we calculate using the stoichiometric conversion factors. Okay, so we divide the actual by the theoretical, and then we multiply that by 100%, which is kind of mimics the percent error that you guys now do in the lab when you compare the theoretical to the experimental. Okay, so we multiply that by 100%, and ideally, the closer the percent yield to the theoretical amount, it means that reaction was very efficient and it was running at its optimum conditions. Okay, so what we need to do first, when we do percent yield, we need to calculate the theoretical amount all the time. Okay, so let's try to calculate the percent yield for this example. So the question goes, if 50.9 grams of aspirin, the C9H8O4, molar mass is already given, 180.16 grams per mole, is produced from reacting 79.8 grams of salicylic acid, the C7H6O3, molar mass is given as well. What is the percent yield from this reaction? So the number that we see here, the 50.9 grams of aspirin, this represents the actual. The actual, that means this is how much was obtained from reacting salicylic acid in a lab. What we are going to try to calculate, we're going to try to find out theoretically how much aspirin we should have gotten if this reaction was running at ideal conditions. Okay, because if you remember, As we said earlier, the percent yield equals to actual divided by theoretical. And then we multiply that by 100%. So the actual we already have here, which is the 50.9 grams. What we need to calculate using our calculations and stoichiometric calculations is to calculate the theoretical if we know how much we are starting with salicylic acid, which is the 79.8. Okay, so if I were to kind of draw a plan or sketch a plan for this, so we are starting with the grams of salicylic acid, the C7H6O3. Okay, I will need to convert that into mole of salicylic acid, 603. And then I'll convert the moles of salicylic acid into mole of aspirin, which is the C9H8O4. And then I'll convert the moles of aspirin into gram of aspirin, which is the C9H8O4. Gram to mole, this is calculated through the use of the molar mass. So if I know the molar mass for salicylic acid, I should be able to convert the grams into moles. Converting from mole of salicylic acid into moles of aspirin, that's the part where it's kind of a tiny bit tricky, because that one should come from the stoichiometric balance of our chemical equation. So if I look at the salicylic acid down here and the aspirin on my products, we can see it is 1-to-1 ratio. That means if I have 1 mole of salicylic acid, theoretically, I should have 1 mole of aspirin in my products, okay? So this will come from the balanced chemical equation. Once I have moles of aspirin, I should be able to convert that into grams using the molar mass one more time, which is also been given to us in the question. All right, so let's try to put this in application. So I'm starting with 79.8 grams salicylic acid, C7H6O3. I'm going to convert that into moles of salicylic acid because, again, my stoichiometric relation between aspirin and salicylic acid, it's based on the mole ratio. So I need to convert the grams into moles. How do I do this? I'm going to be using the molar mass. So the molar mass for salicylic acid states that for every grams of C7H6O3, mole C7H6O3. For every 1 mole of salicylic acid, the mass is 138.12. Again, if you noticed here, I basically inverted my molar mass, and I had to put the grams in my denominator so I can cancel out the grams. I can cancel out the grams of salicylic acid with the grams of salicylic acid. So now I have moles of salicylic acid, okay? So don't get caught up with the how the molar mass ratio look like. You can always change the fraction depending on what kind of conversion you're trying to do. What is the unit that you're trying to obtain at the end? Okay? So now that I converted to moles of salicylic acid, I can convert these moles into moles of aspirin. So for 1 mole of aspirin, the C9H8O4, 1 mole salicylic acid, C7H6O3. So now moles of salicylic acid cancel out with moles of salicylic acid. I am left with moles of aspirin. So I'm almost there, but what I need to do is I need to convert these moles of aspirin into grams of aspirin, right? Because that's the unit that I'm seeking at the end. So I need to have gram of C9H8O4. Down here, I need to have mole C9H8O4. According to the molar mass of aspirin, for every 1 mole of aspirin, the mass will be 180.16. Okay? Again, following up with my cancellation. So what I will do is I will cancel out moles of aspirin with mole of aspirin. Now I am left with grams of aspirin, which is exactly the unit that I am required to reach at the end of my calculation. Now, if you punch in all these numbers in your calculator, the number you'll be getting is the 104 grams of aspirin, C9H8O4. What does this number represent? This is the theoretical. And that should be obvious because we have achieved this number through simply mathematical calculations, right? So this is theoretical. This is the ideal number that you should get if you are to react salicylic acid to form aspirin. But in fact, when they were conducting this reaction in the lab, the number they were getting is the 59 or 50.9 grams of aspirin. So there is about almost, as we will do in a second, almost 50% success of reaching how much they are supposed to get at the end of this reaction. And again, that could be for so many reasons, side reactions, some catalyst whatnot, or some reagent were not as pure as they should be, so on and so forth. Okay, so let's go calculate our percent yield. Our actual 50.9 grams divided by 104 grams. So grams going to cancel out with a gram, 100%. So if you divide these two numbers and you do that on a calculator, the number is 48% yield. And I tell you, in a lab, if you get 48% or even 40% yield compared to your theoretical, this is considered success. Reactions generally doesn't go above 60 or 70% because of the reasons that I mentioned above. So 48%, that's definitely a success. If they are able to get 50% as actual in the reaction. Okay, so this is how we calculate percent yield. So for molarity calculation, this is the last part that we are going to cover in this unit. So up to this point, all the calculation we have been doing mostly is converting between grams of substance to moles by using either the atomic mass or the molar mass, and then converting from one mole of a substance to another, either between the products or between a product and a reactant, using the stoichiometric balance of the balanced chemical equation. Okay. In some instances, reactions take place in a water medium, or what also known as aqueous solutions, as you see here. The reaction of silver nitrate and sodium phosphate. So when you have a reaction that is taking place in an aqueous medium, it would make more sense. It would be easier and more convenient to measure and do the calculations through volume instead of doing mass. So instead of doing grams, starting with the grams, with molarity, we will be starting with mils, okay? Because what molarity means, it's the number of moles of a substance divided in a 1 liter, volume, okay? So a mole of a solute divided in 1 liter of solution. We will use this formula of molarity as a conversion factor to convert between moles of a solute and volume of solution. Okay, so instead of starting with the grams, with molarity, we will be starting with milliliters, and then from milliliters, we'll be able to calculate the number of moles. Let's try to put an example and see how molarity is going to help us to figure out the theoretical amount of moles of either one of the products based on the stoichiometric balance between products, or how much we will be getting in terms of moles for one of the reactants. Okay? So how many milliliters? So every time you see, or the question asks you for a number of milliliters, you should immediately assume that you'll be doing a molarity type of calculations. how many milliliters of 1 molar of silver nitrate is necessary to precipitate the phosphate or the sodium phosphate from 25 mils of 0.5 molars of sodium phosphate. Okay, so we are trying to find out how many milliliters of silver nitrate will be needed to precipitate the phosphates in a 25 mil of 0.5 molars of sodium phosphate. Okay. First thing what I would do, every time you see molarity, please convert this one in a way that you can use it as a conversion factor. How do you do this? 1 molar of AgNO3 using the molarity formula means 1 mole AgNO3 in 1 liter of solution. So now I can use this as a conversion factor to convert between moles of AgNO3 and liters or milliliters of AgNO3. So this is my conversion factor. To convert again between moles of AgNO3 and liters or milliliters of AgNO3. Likewise with the sodium phosphate. So I have 0.5, that's a big M, that's not a small m, and Na3PO4. What this means, this is equal to 0.5 mole of Na3PO4 in a 1 liter of Na3PO4. So I can, once again, use this one as a conversion factor to convert between milliliters or liters of sodium phosphate into moles of sodium phosphate. So essentially, this is almost like it's serving the purpose of the molar mass, but in this case, we're using the molarity, if that makes any sense to you. Okay? All right. So the plan here is we're starting with milliliter of solution of sodium phosphate. I need, in order to find out how many milliliters of silver nitrate, I need first to convert that into moles of sodium phosphate or silver nitrate. I'm sorry. Okay, so converting the mils into moles of sodium phosphate. This will be done through molarity. Now I need to convert the moles of sodium phosphates into moles of silver nitrate. This will be coming from balanced chemical equation. Once I have moles of silver nitrate, I need to convert that into mils of silver nitrate, and this is going to be coming through molarity. Okay? So this is basically my plan to convert between mils of sodium phosphate into mils of silver nitrate. All right, let's try to do exactly what I have just explained. So I'm starting with mils of sodium phosphate. How many mils of sodium phosphate I have? Let's go back to our question. So I'm starting with 25 mils of sodium phosphate. So 25 mil Na3PO4. Now, I can use my molarity, but I have a little problem because my molarity unit is in liters. This one is in milliliters. So then what I need to do is I need to convert these milliliters into liters. So I can use my molarity conversion factor. So this is from our old days of international system, the SI system conversion factors. So I need a liter up here and 1,000 milliliter in my denominator. So I can cancel out the 1,000 milliliter with a milliliter. So now my unit is in liter. Now I should be able to use my molarity conversion factor, right? Which is right here. So 0.5 mole Na3PO4 in 1 liter of Na3PO4. All right, let's make some room here. Now, I need to convert my moles of Na3PO4 because if I cancel out the liters, now I am left with moles of Na3PO4. I will need to convert my moles of Na3PO4, the sodium phosphate, into silver nitrate. Now I have to go back to my balanced chemical equation, okay? And from this one, I can tell that for every 1 mole PO4, 3 mole of silver nitrate is needed. I have 3 and I have 1. Okay, so this one is coming from balanced chemical equation. Now I have mole because mole of Na3PO4 is going to cancel out with a phosphate, with a sodium phosphate. I have now moles of silver nitrate, but I need to convert these moles of silver nitrate into milliliters. Remember, the question is asking us for how many milliliters. How can I convert moles into milliliters? The question is, we need to do this one in red. By using molarity. Because based on the molarity equation, for the silver nitrate, 1 mole, this will be a 1 liter up here. And then down here will be 1 mole of AgNO3, the silver nitrate. If you noticed here that I flipped my molarity for the silver nitrate. Why? Because I'm trying to get liters or milliliters of silver nitrate at the end of AgNO3. Okay? So I need to have my my milliliters or liters in my denominator, and then I have my moles of AgNO3 cancel out with my moles of AgNO3. Now I have liters of silver nitrate. So I'm almost there, but not quite yet, because what I need to do is I need to convert these liters into milliliters. Remember, I need my answer in AgNO3 in milliliters of AgNO3 because that's the unit that I started with. Down here will be liter AgNO3. 1 liter equal 1,000 milliliter. If you put all these numbers in your calculator, the number you'll be getting is 37.5 milliliter of AgNO3 is needed to precipitate the phosphate. Okay? All right, let's try one more example for molarity, and that should seal the deal for us. Same question, same format, and that would basically be your way to tell if you're doing a molarity calculation or if you're doing percent yield by looking at what the question exactly is asking you to do. If you're being asked to calculate number of milliliters, that means you're doing molarity equation or molarity problem, okay? So in this case, we are being asked to calculate how many milliliters of 2 molar of sodium hydroxide to neutralize 25 mils of phosphoric acid, okay? But as you know at this point, without really knowing what is the stoichiometric balance between your products and your reactant, there is no way that you can convert between one substance to the other. Well, what does that mean? That means it is necessary for us to write a balanced chemical equation, and then we can take it from there. So in this one here, we are not given the equation. So we need to write it down, and we need to make sure that it's balanced before doing any of the molarity calculations or any other calculations. So the question is talking about the sodium hydroxide. So sodium hydroxide is NaOH reacting with phosphoric acid. So that one is H3PO4. Okay. This one is aqueous. This one is aqueous as well. We have a base and we have an acid. What is the products? H2O, that's for sure. And salt, Na3PO4. And this one's going to be aqueous as well. Why is it aqueous? Because Na is from group 1 in periodic table, so all the salts are always soluble in water. So now I have my equation, but it's not balanced because I can tell at least for the sodium I have 3 in my products and I have 1 in my reactant. So what I need to do is I need to multiply this by a factor of 3. Now this is going to change the count for oxygen, because if you see here, there's 3 times 1, okay? So that makes it 3 oxygen in the NaOH, plus I have 4 oxygens on the phosphate and the phosphoric acid. That makes it 7, while I have 4 and 1, I have 5. So what I need to do is I need to multiply this by 3. So that should bring, so this should bring up the equation to being a balanced chemical equation. If you double check the numbers for the hydrogen, for the phosphate, for the oxygen, everything should be balanced at this point. Okay? So now I have equation that's stoichiometrically balanced. Now I can establish my relations, mole relations between the phosphate, the phosphoric acid, and the sodium hydroxide into my calculations of molarity, mils into moles, using the molarity equation. Okay? So going back to the question, because at this point we have the equation, we can start doing our calculations. So we are being asked to convert or calculate the milliliters of sodium hydroxide, 2 molars of sodium hydroxide. And again, going by what I had advised you earlier, 2 molar of NaOH, always write that in the conversion configuration. So that would be 2 mole NaOH, 1 liter NaOH. Okay, so that's for the NaOH. For the phosphoric acid, it's 1.5 H3PO4. So that would be 1.5 mole H3PO4 divided by 1 liter of H3PO4. Now I can use my molarity fractions into as conversion factors to convert between moles and liters. Similarly to the molar mass to convert between moles and grams, as I said earlier. So what is our plan here? We are starting with milliliters of phosphoric acid. We're going to convert that into moles of phosphoric acid through the calculations of, or using the conversion factor from the molarity, big M, and then converting the moles of phosphoric acid into moles of NaOH. And this will be coming from the balanced chemical equation. Once I have mole of NaOH, I'll convert that into milliliters of NaOH. And again, once again, this will be done through molarity. Okay, let's now try to do all these calculations together and execute our plan. So I am starting with milliliters of phosphoric acid. What is the milliliters of phosphoric acid? How many milliliters of phosphoric acid that we are starting with? We're starting with 25 milliliters of phosphoric acid, PO4. I need to convert this milliliters into moles. How do I do this? By using the molarity, because I have the molarity here for phosphoric acid. It's 1.5 moles phosphoric acid per 1 liter solution of phosphoric acid. So my problem here, I need to convert my milliliters into liters. So I have 1 liter H3PO4, and I have 1,000 milliliters. So now I can easily cancel the milliliters with the milliliters. Now I have the volume of the phosphoric acid. It is now calculated in liters. So now I can use my molarity conversion, which is, again, I'm trying to convert into moles of phosphoric acid. So I need mole H3PO4. Okay? So down here will be liter H3PO4. Based on my molarity calculation, 1 liter is 1.5 moles of phosphoric acid. Now, I have to use my stoichiometric mole-to-mole relation between sodium hydroxide and phosphoric acid. And I know it is a 3-to-1, right? Because there is a 1 here. So, mole NaOH, mole H3PO4. And based on my balanced chemical equation, for every 1 mole of H3PO4, 3 moles of NaOH are needed. Okay? So up to this stage, what I can do is I can cancel out the moles of H3PO4 with a mole of H3PO4. Liters has already been canceled as well. So now I have moles of NaOH. I am left with one last step, or possibly two. I need to convert the moles of NaOH into liters of NaOH. How can I do this? By using the molarity calculation, the molarity conversion of NaOH between moles and liters. Okay? So again, we're converting the moles of NaOH into liters. So I'm using the molarity. So I need to have liters of NaOH up in my denominator and mole NaOH in my denominator. And based on the molarity that it's already been given to us, every 1 liter of NaOH has 2 moles of NaOH. So what I can do up to this point, I can cancel out the moles of NaOH with moles of NaOH. Now I have liters of NaOH. So I'm almost there. What I need to do in my last step is to convert the liters into milliliters, because the question is asking us to calculate the milliliters. And generally, if you start with the milliliters, you'll have to finish with milliliter, just like with the grams earlier. If you start with the grams, you have to finish with a gram. If you start with a pound, you have to finish with a pound, so on and so forth. So now I need milliliters NaOH. Down here is a liter NaOH. 1 liter, 1,000 milliliter. Now I can cancel out the liter of NaOH, and I am left with milliliter of NaOH. Now, if you put these numbers in your calculator, the number you'll be getting for milliliters of NaOH is 56.25 mils. So, mils. NaOH. Needed to neutralize 1.5 molar of 25 mils NaOH. Okay? Okay, let's sum up everything for stoichiometric calculations. So generally, the calculations will call you or will ask you to convert from the amount of one substance to the amount of another, just like how we did with NaOH and phosphoric acid. We know how much we're starting with phosphoric acid, and we're trying to calculate how much exactly of NaOH will be needed to complete the reaction. So that's between two reactants. In some cases, we need to find out how much of the reactant will be needed to get an X amount of the product, just like the example of the aspirin prior to the NaOH example. Okay, so all our calculation, it really rotates around the concept of calculating how much you will need of one substance to either react or to produce another substance. Okay, general steps. If you're not given it, and that is probably the most important step when it comes to calculating doing stoichiometric calculations. If you have not been given the equation, the balanced equation, you will have to write the equation and you have to make sure that it's balanced. Because as you know, up to this point, with so many examples we have done, in order to convert from a mole of substance to a mole of another substance, we need a balanced chemical equation. So you need to make sure to write the balanced chemical equation. That's number one. Okay. Number two, you will convert from the units that you are given of substance one to moles. So generally, I believe all the times what we do is we convert to moles of that substance. So if you're starting with the grams, you'll have to convert the grams into moles using the atomic mass or using the molar mass. If you're starting with the milliliters, just like with the molarity, you'll have to convert the milliliters into moles using the molarity conversion factor. Okay, so for solids and liquids, we convert the mass into moles using the molar mass, or sometimes we use also the atomic mass if it is just an element. For solutions, on the other hand, we use the molarity to convert from volume of solution to number of moles. Now, once you have converted the quantity that he started with, or the unit that he started with, into moles of that substance, now we need to convert from substance 1 to substance 2. And this one comes from the balanced chemical equation. This basically comes from step number 1. Once you convert to substance 2, now we'll have to convert the moles to the desired unit. So either the grams using the molar mass or converting from moles into milliliters using the so this one here, this is like the grand finale for everything that we have been talking about. This basically summarizes everything. So if you go through this sketch, this basically goes through everything and all the calculations that we have been doing. So generally we start with mass of unit 1, either convert to grams using the molar mass, or we convert to moles using the molarity. Okay? Once you convert to moles of substance 1, you'll have to convert to moles of substance 2. This one here comes from the chemical equation, the balanced chemical equation. Once you convert to moles of substance 2, now we'll have to convert to the desired unit. So either you go to the mass using the molar mass, or you go to volume using molarity. Okay? And this one is using the molar mass. And this basically should take care of Unit 9. Again, please, if you have a question or there's something that is unclear, do not hesitate to send an email or even stop by after the lab and ask a question. But please do not sit on something that you're not familiar with and just wait for the exam to come in. Okay?